Hi folks, today I wanted to talk about a new type of type annotation that is currently in development. Its placeholder name for a couple years now has been TypeForm, but there's a fairly good chance, as I'll discuss a little bit later, that it may end up getting renamed to something else while it's in the middle of being finalized. So currently, there's a second draft of a PEP for this, and we're still undergoing some feedback. So I introduced myself a little bit earlier. I'm David Foster. I've contributed to MyPy, and in particular, I did the initial design for type-to-dict and one of the early implementations for it. During my work days, I am hoping to inspire the next generation of K through 12 students to write code and do cool things with computers. So the way I wanted to structure this talk is, first I wanted to talk a little bit about what is the current definition of typeform, why is it useful, and then I wanted to break out some time at the end for a more extended discussion on some open questions, controversial points that are related to the design of this feature since it is in progress. So, what is a typeform anyway? The very short answer that I've been coalescing around is that it is what the typing specification calls a type expression, which is any kind of type annotation object which describes a type. So this is more than what the phrasing type T currently describes, because a type T only accepts more simple class objects, your basic integer, but type expressions is anything that a static type checker would consider to be a more interesting type. So you have your generics, like list of int, you have type-to-dicts, you have many forms of unions, pipe operator, union special form, literal special form. So this more broad set of types is encompassed by type expression and therefore also type form. There are also, I should mention, annotation expressions, which are things that can appear in the location where an annotation is expected, but they're not always valid in other locations. They are only valid in certain contexts. Final int can only be used on variables. Required can only be used on type-to-dict items. Class var can only be used in the bodies of class expressions. So annotation expressions are only valid in certain contexts. I will mention that there are some type expressions that the typing spec puts forward that are also only valid in certain contexts, so they are considered to be a type. I think they're a little bit more interesting, so I end up having to consider them a little bit more specially later. Specifically, it's self, type guard, and type is. So there are also some type expressions which generally are considered equivalent to simpler expressions, and all of these present some complications later. You have stringified types, you have annotated types, which are roughly equivalent to the type that they are wrapping, but they also add some metadata. And none is a little bit interesting because it's an alias for none type. So, and all of these at runtime can actually be stored. Like you can take an int pipe stir and set it to X. You can set it to a variable, and this is actually used a lot by runtime type checkers. So all of these are objects. They just don't happen to be your regular value type object that you run into most of the time. So that's a little bit about like what type form, type expressions are intended to represent. Why are they useful? So I thought I might want to explain that a little bit by showing one of the initial applications I had. So early on when I started to put type-to-dicts into the spec, I wanted the ability to take data from JSON APIs and be able to use a Python type system to be able to check whether a value coming in from JSON was equivalent to some type of thing that I could spell with a Python typing system. So I wanted the ability to write a shape like this, such as a movie that's coming in from JSON, and I wanted to do something like ask whether a piece of data coming in from a JSON API is an instance of that type. However, there is a problem. You can't actually use isinstance on something like a typed dict or a union type or many of these more complicated type expressions. You'll get a type error because isinstance only works on simple class objects. So to solve this problem, I made a function called isassignable, which is very similar to isinstance, but it works with any type expression object at runtime. And with isassignable, you can just replace isinstance with isassignable, and that part works. So that works at runtime. It will return true if it is in the shape, in this case, of a movie. However, there's another problem. So the assignment right after it doesn't work from the perspective of a static type checker, because a static type checker cannot tell that because isassignable returned true, it should be safe to narrow the type of the data argument to be movie and not just object. So what do we do about that? By contrast, isinstance, you can do that for simple types. It will actually type narrow. So why? Why is there a difference in behavior? So isinstance conceptually has a definition similar to the top here, where it explicitly takes a type T, a class object, a simple class object, and its definition uses that in combination, again, conceptually with type is to allow the first argument to isinstance to be narrowed to that type T when the function returns true. So if isinstance returns true, type narrowing is allowed. I would like to have something similar that would work not just on simple class objects, but also for arbitrary type expressions. Right now, I can't actually spell a type expression, so I'm forced to annotate it as taking a object where I would like to annotate that it takes a type expression. In a world without typeform, this is the best you can do. So in a world with typeform, we would annotate isassignable to take a type expression, take a type form, and then we could use that in combination with other features, in this case type is, to say that it will narrow the type of its value argument to match the type expression if it returns true. So this is one example of a function that you can write and type annotate with something like typeform and get an improved, in this case, an improved type narrowing behavior. There are several other functions that you can write that usually come up in the context of runtime type checkers that would be able to use type expression in a similar way. So like you have a converter, you'd have this in Pydantic, for example, a type adapter, I believe it's called. You could say, hey, I want to take this arbitrary value and I want to convert it to this type, and if it actually matches that shape, then give it back to me. Otherwise, raise an exception, return a none value, that sort of thing. So there are various types of functions that I've seen in multiple places, mostly in runtime type checkers that could benefit from this type of thing. So that's a little bit about the design so far. So I wanted to take on some discussion topics. So I'm open to all topics, but I wanted to highlight a couple points that have been a little bit more like open questions, controversial topics that have come up during the design review process. And in many cases, I have like a very quick, sort of like simple answer for a couple of these items, which I'll go over briefly first. I have some initial thoughts. And after I've gone over sort of my like initial thoughts on a couple of these areas, wanted to open up the discussion to everyone in the room. Maybe we'll have a mic passed around to folks who raise their hand and see what you think about any of the controversial topics or anything else that you want to mention that would be useful to talk about in the context of designing this new feature. So very quickly, what is this thing even called? Right now we've landed on it being pretty close to matching a type expression. So that sort of implies to me that it's probably called type expression, or maybe the shorter type EXPR. How should annotated be handled with this? Should it even be allowed to be matched? Will it strip out the metadata in some way? So should it match? Yes, it works naturally when matching a type expression. The question about what it does about the metadata is a little bit more interesting. Stringified type expressions, these are exceptionally difficult for a runtime type checker to handle. So should we allow a type form to even match these? And right now my default is that we should allow it to still match stringified type annotations, even though it's difficult for a runtime type checker to deal with, because that avoids us creating something that's like smaller than a type expression that type form corresponds to, rather than just having it round to the nearest. We want to round it to a type expression or an annotation expression or something that's already defined, rather than creating a whole new category of things that we have to explain, which is it's just difficult to tell people about when you have too many concepts. So, and I also wanted to point out that runtime type checkers already can't deal with certain types of values. Stringified type annotations are just another complication. So it's another. This is not a special thing that is new and difficult to process with the runtime type checker. So there's a longer topic about should we allow matching some subset of expressions. So there's a specific syntax that was put forward where you have type form matching origin type and some archetypes to kind of pattern match a specific type of type form to be expected. So right now I've sort of defaulted to it's probably we should just recognize the expressions in general and not try to sub-pattern match it. It would be difficult to write a formal language that would match the specific subset of things that people want to match. And the last topic, which I won't go into too long, implementability. Like, can we actually implement this in things like PyWrite, MyPy, etc., given certain constraints? And right now, I'm talking with specifically Eric about his concerns in PyWrite. For MyPy, I'm thinking I'll just try and draft an implementation and see if I run into issues. And there may be other issues that people have that relate to implementabilities, especially we have many folks in the room from the Pirate team here, so that's pretty cool. So I'm just going to leave this slide up, and we have now 15 minutes for discussions.
Thanks. I had a different question about implementability, but what do you actually put in the body of a function like isassignable? Do you have an example of that?
So the main The main case where you would write a function that would take something like a type form is something that actually knows how to deal with, it actually knows about all the various different typing special forms. So this is usually in the domain of some kind of runtime type checker. So someone who's declaring a function like this, they are taking on a significant burden. And there's a section of the PEP, how to teach this, which tries to highlight that most users of this will be calling functions that have these definitions, but you're probably not implementing this yourself, because actually trying to examine a value of type form and make decisions based on it is a significant burden to take on, because you do have to know what all the typing special forms are effectively.
Are those APIs even in the spec?
Could you rephrase the question?
So I seem to recall that you have to look at various dunters and of course do an isinstance to say determine whether something is a union or a generic type or many of the other things. And then once you know what it is, you have to sort of know, oh, if it's a union, it has a certain dunder that is a list of the types that compose the union. That all, I think, is not in the typing spec. I think Shantanu understands the question and has an answer.
Yeah, it's not in the typing spec, but there are public APIs in typing.py for this, like typing.getOrigin and typing.getArgs. In general, runtime type checking is not possible. Like usually the kind of things you do here is you special case a few sort of types of generics like sequences and maps and type dicts, and you just like check all the collection values. But
I mean, yeah, that's something where, like Shantanu said, there's public APIs. We can make it work. Of course, we'd like it to be like maybe more formalized and better documented and stuff. But like, ultimately, like Pydantic's taking it upon ourselves to discover how to do those things, and it works for the most part.
Yeah, just on the Pydantic subject, we have Type Adapter, which works today, does this. In fact, it was working with Pywrite, so if you gave Type Adapter a union, it would say that the value you got back after doing the validation was a union, and now that has broken for good reasons because there was no type form. So from our point of view, we just need the thing so that static typing can match what Pydantic can already do in this case. Carl had a question.
Thanks for the talk. I guess I'm curious, so given the usage scenario that you outlined, I'm curious what all you're expecting from static type checkers in terms of checking type form. It seems clear that what you most want is for, if you have a type form annotation, for static type checkers to verify that a caller is providing something that is a valid type form. Within the body of your isassignable function, how do you want static type checkers to treat type form? Should it essentially be any, or should they try to understand all of the possible special forms and validate your checking of them? What do you expect from type checkers here?
Yeah, so the current draft of the PEP specifies some interactions with other features such as type is, type guard, which is similar, and type variables. So there's the ask on static type checkers is to, in the case of type is and type guard, to support certain types of narrowing semantics. I guess there's perhaps a little bit less interest necessarily in recognizing that, like, you have a variable of type form and it is assigned something that is known to be a type expression. This is valuable in and of itself, but it's really a static type checker needs to know, if you're combining this with something like type is or type guard, it needs to understand the value that's being passed in, usually a literal type expression. It needs to understand that well enough in order to make interesting inferences. So hopefully that partially answers.
I think Shantanu has it. I mean, that doesn't quite, I mean, that all makes sense. I think type checkers already have to understand things like that to support cast, for instance. What I more meant is, like, if you have isassignable and it's taking in one of these expressions, what do you expect type checkers to check within the body of isassignable as you're making use of that type form that was passed in?
Not much of that.
Okay, that was what I thought.
Yeah, that covers it. Like, I think the main value is being able to destructure, to associate the value of a type var with the type form and the actual like runtime type checking code. We shouldn't static type check. It's going to be horrible.
Okay.
Generally, it should be treated as object, so it can't make many assumptions at all. And so a runtime type checker already has to do a bunch of assumptions. It has to do a bunch of casts and other types of things.
This jumps a little bit away from this previous topic of discussion, but I was curious, I'm a little bit uneducated on the specifics of this, but with regard to stringified type expressions, is there any appetite, I guess more broadly, for moving away from stringified type expressions entirely?
Yes.
Broadly, yes. We've made a lot of changes to the language and the ecosystem to make them less necessary. Hopefully in Python 3.14 we have PEP 649, which will mostly make them unnecessary. But they exist. There's always going to be a few edge cases where you still need them, because sometimes type expressions are evaluated at runtime. So yes, we should try to design the language so you usually don't need stringified annotations, but there's a lot of code that already uses them, and we need to continue thinking about them.
Just to hammer the point, the landing of deferred type annotations, which I believe is a Python either 3.13 or 3.12 feature, should greatly reduce the need for stringified type annotations in new code, but there is a lot of old code that still uses them.
And just to be clear, what we're talking about is PEP 649, the variant evaluation of annotation. It was supposed to happen in 3.13, it's not happening. I will make sure it does happen for Python 3.14. So in a year and a half, we will have that.
+5 for some people.
Yes, so yeah, I'm not entirely sure I understand what the argument of typeform is. So is it roughly that a typeform is anything that can be bound to a type variable, and the argument is just a type variable to capture it?
Yes, it's anything that can be bound to a type variable, which, according at least to the current typing specification, is a type expression as it defines.
All the examples I've seen and all the use cases I can think of, it's you use typeform, like you said, in the argument to like is assignable or something like that. I assume there's no logic, but I've also seen no prohibition of like using it in a return value or something like that. I don't have a use case for it. I'm just, maybe it should be explicitly prohibited. I don't know.
I don't know of any specific real-world usages that involve returning a type form. If it would make things easier to ban it, that would make sense to me. If banning it would make the behavior somehow inconsistent with how things normally operate, more or less I'm open to doing whatever's the easiest.
I could imagine it being useful, like, we say stringified annotations are a problem. Maybe you would write a helper library for things like identic or tricast that takes in a type expression and returns another type expression that has gotten rid of all the string annotations. So I think it could be useful. So you could write like isassignable on something that's unstringifies the annotations.
Or simplifying, changing generics. Which
Yeah, you can imagine there is ways to like simplify annotation or something.
So yeah, just one quick question about implementability. I think Eric has that question, right? Like when I see something in my abstract syntax tree, do I treat it as a type or do I treat it as a value? I think this is a very right now, like without typeform, this is a very straightforward answer. You just they're fixed places. Yeah, they're casts, right? But when you see the cast, you know that a cast has a.
Well,
Okay.
how do you know
it
it's
could be
typing the
cost
cast?
equals 5.
How do you know a function call is called to typing.cast? Because if it's called to typing.cast, then you're writing this type expression.
Yeah, do we follow the same rule here? Is the
Do you know what Pyre does?
I know what Pyre does, and it's not simple.
Interesting.
So the answer is basically whatever task you do.
So I'll dive on this a little bit because I actually have supporting slides. So the question again is around Eric's concern, like how do I know just looking that this thing is supposed to be either a regular garden variety value or is it supposed to be like a type expression, which is in the more restricted syntax. So there's the short answer. So this is a work in progress, but right now my initial thought is that you have these special forms. They do work at runtime. They actually are things at runtime, and so you can probably parse them initially as value expressions. And in many cases, even just looking at the special forms, you know that the special form is ultimately, at least conceptually, a kind of type form. So it could be sort of like a virtual superclass of some kind. That works for many kinds of type expressions. It also works, I hope, in cases where you know that you're naming a type var. That kind of can be seen as like having a type form as a virtual supertype, type aliases, regular type Ts. Things where it gets a little bit more complicated is things like none, because none by itself can be interpreted as the none value or can be interpreted as the none alias that means the none type. String literals are particularly tricky because it could just be a garden variety quote words, or it could be a quote complicated type expression. So that's a more tricky case to deal with is string literals. And something that's also a little bit difficult is specifically the pipe operator. Capital Union is great, but the pipe operator, you're not quite sure whether it's like, if it's like I don't know if it's a bitwise operation. Is it a bitwise operation, or is it you actually have to look at the two sides in order to figure out is the left side and the right side a reasonable type expression in order to figure out whether the top level thing works. So yeah, those are the interesting cases.
Maybe you just covered this, but it's suddenly thinking about this. Does that mean we could do isinstance typeform and use that as a reasonable check? And is there a world where we go further in future? Okay, well, Guido's saying definitely not, so we'll back off from even saying the next stage.
Yeah.
Off the top of my head, no.
Yeah, not proposing it to work at runtime.
Okay.
But this is why I said virtual supertypes.
Okay.
We're actually out of time, I think, for this talk. Thank you, David. This was very helpful.